Now here we are going to look at the fluorescent excitation as absorption spectra and versus the emission spectra. Okay, so here this is absorption is actually plotting the excited the absorption process, right? Okay, it's get excited. So we are looking at the excited states. So as you can see, all those molecules, all this molecule is start from ground states, and the purple have higher is the second excited states is happening, and the blue here is happening at the first excited states. Okay, and the blue is much stronger energy than the blue one. Okay, when we are looking at fluorescence emission, fluorescence is a process which is the emitting process. So we're looking at how the molecule coming down to the ground. Okay, they all start from the lowest excited states and they coming down to the different level of energy level stage. Okay, so it's all starting. So the fluorescence emission spectrum is looking at from the lowest excited states and coming down to the lower energy states. Okay, it also will happen if it's doing some internal intersystem crossing. It will have it's in the triplet state, and then what phosphorescence looking at is also from the lowest triplet state, triplet state, how this coming down to different energy level. Okay, that's what it's probing. Now, if you just compare of the absorption process and fluorescence energy level, you can see that absorption is always higher energy than fluorescence. They have some overlap, but majority of fluorescence absorption should be lower energy, right? So here, this is so why is that? We can see from here, this is starting point. Okay, so for example, your molecule, starting point, you absorb the photon, so it goes to the excited stage. And by absorbing this energy, right, you will relax down to the lowest excited stage. So you are losing some energy here, right? So when your fluorescence coming down, the energy should be from fluorescence should be smaller than absorbs, right? You have some overlap, but the majority of the absorption should be higher energy than compared with the fluorescence emission. Okay, so this is how you can see the absorption. You have some of the overlap, little bit overlap, but absorption majority is on the lower wavelengths, which is higher energy, and fluorescence is a larger wavelengths, which is lower energy. Okay. Now, for those absorption, fluorescence, phosphorate, how fast it happened. This is a time scale. Just want to give you some idea. It's for the fluorescence. So for absorption, it happens the most quickest. It's 10 power negative 15 seconds. And the relaxation and internal conversion, it actually happened on 10 power negative 12. After that, the fluorescence happen is 10 power negative 9. So it's really fast. And phosphorescence is more than 10 power negative 3 seconds. So it's a very much longer process. Okay. So because the fluorescence happens so fast, so your eye cannot really tell the you think it happens immediately, so it's actually 10 power negative 9. But fluorescence, because it takes much longer, your eye can able to observe the whole process. Okay. So first we are going to introduce is this Jablonski energy diagram, okay? And this is very important diagram to explain how light interact with matters, okay? You can see here a lot of lines. Each line replaces energies, okay? And the line goes up, the energy increase, okay? The bottom is the ground, the lowest energy level. Now, there are different things. There are many things going on here. So first, let's take a look what is blue means. The blue arrow means the processes that involves photon, so light. Okay, and with this red squiddy arrow, means the radiationless transition. So it's not photons. Radiation transition usually is like heat. Okay. Now let's take a look of process 1. This is an absorption process. Okay, one absorption process. So when the light interacts with shining into the matters, the molecules will get excited. Okay, so it will absorb the energy from the light and excited to the excited state. Okay, to a higher level. And then what they will do is to have some vibrational relaxation into a certain stage. Okay, this vibration relaxation is usually heat. And then coming down here, if it goes process 2, which is fluorescence. So some material, they have fluorescence property. They will absorb the photon, like process 1, and then here release the rest of the energy as a light. Okay, this is what we are using. This is what we are measuring in this lab. Okay, but a lot of materials, they are not necessarily have fluorescence. So how that energy go? There are several possibilities. Okay, so a lot of chances that they will have internal conversion. So it goes to the lowest state of the excited state, and you convert to the grounded electronic states. Okay, internal conversion, IC. Okay, and then you will dissipate the energy as a heat. One example I was thinking about is during summer, it's really hot outside, and you wear a black shirt. So a lot of sun goes to the shirt, is released as a heat. Okay. Now there's another example possibility is it will do a intersystem crossing. Intersystem crossing. That's just ISC. Okay. Instead not mixed with the IC. If in that case, it will goes to from a singlet when it's converted to this ISC, the singlet state will become a triplet state. Okay. What's that mean is that the spin of the electron stage is changed. Okay, like right here. So we know from the Jenkins that the spin of the electron on the ground state is the opposite direction, right? When it gets excited, usually the spin direction is not changing. Okay, so you go to, this is a singlet stage. They maintain the same spin direction. However, when it goes to the intersystem crossing, the spin direction will become the same. Okay, so then in this case, it's harder. It's not going to coming back because they are not supposed to be the same directions, right? So it's forbidden. So this process. So what happened here is that they will relax. So into the triplet state, they will relax back to the lowest stage of this triplet state, and then in order to coming down, and they cannot go to other places because there's no overlap. In order coming down to the ground state, the spin need to changing back to the same the original direction and slowly coming down as a photon. Okay, and this is process 3. It's called phosphorescence, and it usually much longer. This process is much longer than fluorescence. So fluorescence is a very quick process, but phosphorescence is very slow process. Okay. And also here you can see this is one thing is very long time. The other thing is much lower energy for fluorescence. For phosphorescence happen compared lower energy compared to fluorescence. Okay, we actually have maybe everybody have this kind of experiences. When we are little, we usually have those like fluorescence stick. You turn on the light for a while and you close it down. If you post this sticker on the wall, and at night it actually still have some light is shining out. It's still visible, right? And that is because it's phosphorescence. So you open the light, shining the light on the sticker and turn it off, and this for phosphorescence will continue growing, will continue emitting the light. Okay. So for the final, one of the things you have to pay attention is I will for sure have some questions about drawing the Jablonski diagram. Okay, you need to at least know what is the process of absorption, what is the process of fluorescence. So you go absorption, relax back, and have fluorescence emission, and you also need to know what is the internal conversion, what is the intersystem crossing, how to get phosphorescence. Besides that, actually, usually we will talk about the different Stokes, like Raman scattering, Stokes Raman scattering, anti-Stokes scattering. But since we didn't have the Raman lab this time, you don't have to worry about this in the exam. Okay, you just need to study about this Jablonski, the main process for this. For now, you don't have, for this quarter, you don't have to worry about it. Okay.